Question 7. The table below contains a number of radioisotopes. Comment on whether these types of isotope are suitable for any medical scans. So we might just want to list what ones we want to think about. Over here at the side, we have our X-ray scans, which fall into the shadow graph or more complex CT scans. We have ultrasound, in which we might want to keep in mind the idea about A and B scans. We also have Doppler scans. We use gamma rays. We have the simple gamma camera, which produces a two-dimensional image. Or we have SPECT, single photon emission computed tomography, from which we can build our three-dimensional images through scanning from multiple different angles. And we have our positron emission tomography, where again we are using a ring detector to detect pairs of photons that are produced through the annihilation of positrons. This is positron emission tomography. So this is a good place to start in terms of this. So just types of decay initially as we look down this list. Well, beta minus doesn't feature on our list anywhere as a type of radioactive decay we typically use in imaging. So that's probably a good place to start. Carbon 14, beta minus emitter, which is not used for imaging. Then we've got two beta plus possibilities here. So to understand this, we might want to kind of remind ourselves of what a PET scan is. So in a PET scan, you inject a beta plus emitting isotope. The beta plus particles emitted will annihilate with electrons close to where they were emitted. This produces a pair of high energy photons and a ring detector finds pairs of photons and sort of traces back to the point of emission, and then through this process we can build up an image. So this is useful for us to think about, because we want to decide of these two isotopes which one's going to be most appropriate. And at this point we can look at the half-life. And since we inject a beta plus emitting isotope into the body, then a half-life of 13 hours sounds much more sensible than a half-life of 271 days. So a half-life of 13 hours, it should give sufficient time for the radioactive isotope to move through the body. So when we inject it, it needs some time to get to the site that we want to scan. but also will be will not remain radioactive in the body for too long. So we probably just want to summarize this and say iodine 123 sounds like a good bet for positron emission tomography. And then for our first one, our last one, sorry, our lead 207. Well, we do use gamma in gamma cameras or in SPECT imaging. The process is very similar to the one that we've just described. So this does require, again, injection. And we can see that the half-life, is much too short. So it wouldn't have time to move through the body to get to a appropriate place. There's a couple of isotopes that we typically do use. So technetium 99M, and one of the other ones that we sometimes talk about is indium IUM 111. Indium 111 has a half-life of 2.8 days. So that's fairly commonly used. It's quite a long half-life for using inside the body. Technetium 99M has a half-life of about 6 hours. So that's a more typical half-life for something that we're happy to inject inside the body.